and welcome back to 7th grade science. Last time we talked about fossils part 1, and today we're talking about fossils part 2. Up first, we're going to talk about relative dating, and this also includes relative age. We'll cover all of that, and then we're going to end up on the geological timescale. So to start off with relative dating, we're going to talk about some core concepts, and a lot of these concepts are called laws. These aren't necessarily laws like you have to wear a seatbelt while driving. In science, a law is really just a description of an observed phenomenon. Basically, this just means that it's a description of things that we have noted over different periods of time, different events, different things like that. Known phenomenon. Up first, we have the law of superposition. We can break this down. So we have the words super and position. Super isn't used like superhero. In this sense, super is relative to location. So if something is super or superior to, it's above. And then position really just refers to the word position. So the law of superposition is talking about the age of rocks based on their location. Essentially, the older the rock is, the closer to the bottom it's going to be. The younger a rock is, the higher up it is going to be. That's not always the case though, and we'll talk about why in a few minutes. So with rocks and relative dating, you have relative age. And the relative age of a rock is just the age of that rock in comparison to rocks that are surrounding it. So if I have a rock here, and then a rock from up here in a higher layer, the relative age of the rock is this one's going to be older and this one's going to be younger. And the reason being, with the law of superposition, the lower a rock is, the older it is. Because remember, layers build on top of one another, so the newly formed layers, or the most recently formed layers, will be up high, so that's why they're considered younger. Whereas the layers that were formed longer ago are older. Next we have the law of lateral continuity. Well, lateral is referring to horizontal, and continuity is just continuous. So all this concept is saying, or all this law, this concept to relative dating is saying, is that rocks form laterally in continuous layers. Now, when I'm talking about rocks in this sense, I'm not necessarily talking about a single rock that is outside on the ground that you pick up. I'm talking about the rock layers that have formed over years and years and years, building up the ground below us. If we were to dig straight down with a drill, then, and it's wide enough that we could see layers in the bedrock, the rock of Earth, below the soil and all of that. Or I keep using the Grand Canyon as a really good example. Those large horizontal layers you're seeing show the law of lateral continuity. Next up, we have the laws of cross-cutting relationships. And what this name implies is that you have things that cross or cut across other things. And in this case, the things are rocks. So depending on different geological processes, you can have rocks cut across one another. So we could have a layer here, and then a layer here, and then a layer here, and all of a sudden we have an earthquake. So we have a new rock layer form here, and it's going to be younger than the rock layers here, here, and here because it formed after, but it was due to the earthquake. Now that's just one example. There are other examples that we'll cover as we go on. The most important thing to remember with this is the rock that gets cut is older than the rock that does the cutting. Now, all of those laws together are all concepts of relative dating. Collectively, those are known as the laws of stratigraphy. So just to reiterate them, we have the law of superposition, the law of lateral continuity, and the law of cross-cutting relationships. This one's not a law, but it is another concept of relative dating. That's unconformity. And all unconformity is a gap in the rock sequence. What this means is we could have rock layers form. So let's say we have layer A, layer B, and layer C all form. And then due to weathering and erosion, rocks are broken down. So instead of being a nice even across, we now have a shape that's like this, where it cuts down through C, B into A, or 1, 2, and 3 if we're talking about layers that way, and then up. So we have rock layer A down here, or 1, B here, and C here. Now the spot that you can see where you see my nose is a gap. If weathering and erosion didn't happen, then the space would have been flat and you wouldn't really see my nose. But instead, due to weathering and erosion, we have a gap. So the space that you can see my nose is an unconformity. Weathering and erosion is just one way that could occur. You could have plate tectonics causing slips, or you could have earthquakes, and those are all things we're going to cover later. But just know that there are things that happen that can cause unconformities. And what's an unconformity? Yes, it's where there once was rock, but then there is a gap in the differences of rock ages. Now, with our layers, and it's like this where you can see my nose, new rock can form up here where my thumbs are. So that would be rock layer D or rock layer 4. Now, when those form in this area and it comes across, instead of being nice, level, even things, it would kind of be, we have A1, B2, C3, D4, but then also cutting down in would be D4 because that rock layer would build. Let's review those concepts quick. Relative age of one rock is the age of that rock in comparison to another rock. The older rocks are below the younger rocks, generally speaking, and we know that something must exist before it can be cut through. So that's with our law of cross-cutting relationships. We know that it has to be in existence before the rock can get cut. So if we know the rock that is cut, we then know which one was older, because you can't cut through it if it doesn't exist yet. Now, how would we use relative ages? Or why would we use relative ages? Well, if we are looking in an approximate area, so if we're looking around New Berlin, and we want to figure out the age of part of the rock bed beneath the school, we can use relative aging to figure out which one's younger, which one's older. You know, compare the layers, which one's deeper, were there any cutting action that occurred or anything along those lines. This is relatively easy to do for one area. What that rock layer shows us is kind of a snapshot of the history of that time. If we had any fossils or anything in it, or anything along those lines, we would be able to see that in there. Can we necessarily use relative aging to determine the age of rocks here in New Berlin versus in Egypt? Not exactly. So it's very easy to determine the age of rocks when they are relatively close to one another, but when they're far apart, scientists do it a little differently. What they do is something called correlation. And when it comes to geology, they're correlating or relating things found in one area to things found in another. And we've already talked about one important thing that helps do this, and that's index fossils, which we'll review in a minute. To correlate the age of a rock or a rock layer, something distinctive has to be present in each of those layers. If we compared rocks with nothing distinctive, it'd be like comparing apples to oranges. You can do it, but it doesn't really tell you much. Like we talked about the other day, and like I said a few seconds ago, index fossils are a good tool that scientists can use to correlate the relative age of rocks from different areas. So remember from our discussion about index fossils, in order to be an index fossil, it has to be something that's widespread, more than just in one small area, and it has to live for a relatively short amount of time. Now, the examples with trilobites that I gave, the relatively short period of time was 100 million years, which to you and I seems like a big difference, but in the grand scheme of rocks, remember, that's not a huge deal. Or in the grand scheme of organisms in general, 100 million years is not a huge amount of time, which is kind of a weird concept to think about. 100 million years is a lot. 100 million anything is a lot. So these index fossils wouldn't be index fossils if they weren't found in the widespread area, and the reason that that's important is because, again, if you're comparing New Berlin to Egypt, they're not close to each other. They're not even close to each other on a piece of paper map, let alone in real life. So in order for something to be present there as well as here, it would have to be widespread. Index fossils are only one type of thing that they use to correlate the relative age of rocks. Another type is a unique rock type or unique rock sequence. Now, how could a unique rock type or unique rock sequence help? Well, if there's not much of that rock type in existence or that rock sequence, then it would help identify because it's not a lot of it present. If you know that here in New Berlin it was present approximately 23 million years ago, and you find some in California, and then you find some in South America, and that's really the only places you're finding it, you could approximate that it's likely 23 million years old. A good example of this in real life is chalk cliffs. There are chalk cliffs that are found in Denmark and in Dover in the United Kingdom. I also believe Belgium and France are involved in there too, and there's a channel that has been carved through those chalk cliffs over time, and those chalk cliffs are present in those different locations, and they are arguably relatively close on a map, at least closer than New Berlin and Egypt, but they're not right on top of each other. Those chalk cliffs are really similar, and so they can be used to identify the age range because they're in those different locations and they're unique. Then we also have something called key beds, and they're not little tiny beds where you keep your keys at night to keep them comfortable so that you can't find them in the morning when you go to start your car. Key beds are little thin layers of rock that are relatively widespread. A good example of a key bed that's relatively widespread across the globe is a clay layer that's filled with iridium. Now, iridium was present from an asteroid, and this correlates very well, one, with rock ages across the widespread area, but also it correlates with the theory that dinosaurs were killed off by an asteroid. In order for the iridium, which is found in the asteroid, to be spread in that clay layer, it would have to get in the atmosphere somehow. So, as the theory goes, an asteroid comes down that was large enough, it hits the Earth, and then from there, dust and debris goes up into the atmosphere, blocking ultraviolet radiation from coming through, and the dinosaurs die off. Now, that goes along with what we can see in the rock bed as far as the clay layer containing iridium. Because for it to fall under the definition of the key bed, it has to be widespread. And if this spreads across the entire globe, then some type of event had to get it there. So the theory of how dinosaurs became extinct ties in really well with how iridium is widespread. Because remember, if that asteroid hits, and then from there debris is in the air, it spreads around the globe in the debris, that debris will settle, and when that debris settles, it helps form what type of rock? Sedimentary rocks. And then from there, those sedimentary rocks have layers built on one another. And so we have our layer of clay containing iridium that is found in the bedstone. All right, now we've talked about relative dating and relative age, correlation, all of that stuff. Let's talk a little bit about the geological timescale. So the geologic timescale divides Earth's history into separate components. And these separate components are named units. These different time periods all have different names. Now, these time periods and units are all separated by different major events that happened in Earth's/life's history. As we go down, we have large categories, eons, which we'll cover what they are in a second, and then they get broken down into different groups and then different subcategories from that. Essentially, they are just divided and subdivided each time. So we start with our eons, and we really have what could be seen as 4 eons. We have our Pre-Archean, our Archean, our Proterozoic, and then our Phanerozoic, which is the one that we're currently in. Besides Pre-Archean, all of those are broken down into different eras. So the eon Archean is broken down into early Archean, middle Archean, and late Archean. And then the eon Proterozoic is broken down into early, middle, and late Proterozoic. Now, those aren't broken down further. Our next breakdown is from era to periods. Pre-Archeans are just Pre-Archean. And then we have our Archean and our Proterozoic eons that are broken down into early, middle, and late eras of each of those. But they're not broken down into periods. Now, the Proterozoic occurred approximately 570 million years ago, and so Archaeon's older than that, and Pre-Archaeon's older than that. But approximately 570 million years ago, time started getting broken down. We had eons, then eras, then periods, and then something that's called epochs, but also scientists just refer to them as early and late, kind of like we did with the Archeans, but no middle, really. If you want to get super specific, you could break it down to middle, but generally speaking, it's just early or late that scientists use. So the eon that we're in right now is the Phanerozoic. Then this gets broken down into 3 different eras. We have our Paleozoic, our Mesozoic, and our Cenozoic. Now if you've noticed, I'm listing the older ones first and then working my way up to the newer ones. So the Paleozoic time period ran from 240 million years ago to 570 million years ago. This era has been broken down into 7 different time periods. These 7 different ones start with your Cambrian as the oldest, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, and I'm not talking about kind of person, and Permian. I listed those in order from oldest to newest. Remember, so Cambrian started around 570 million years ago, and Permian ended about 240 million years ago. So the Paleozoic era lasted approximately 330 million years. Whereas the Mesozoic, which is the next one in line, lasted only approximately 74 million years. So that was a big difference. Remember that these are broken down by different major events that occurred in Earth's history. So between that time, those major histories were relatively closer together. The Mesozoic is broken down into 3 different periods. You have your Triassic, Jurassic, yes, like Jurassic World or Jurassic Park, and your Cretaceous. And then even more recently, we have our Cenozoic, which is from approximately 66 million years ago to now. And I keep reiterating that these periods are broken down by major events that happened in Earth's history. Does anyone remember what happened approximately 65 million years ago? Dinosaurs went extinct. At that point, we changed from Cretaceous to Tertiary. As of right now, the Cenozoic era is broken down into 2 periods, the Tertiary and the Quaternary. And again, this ranges from present to approximately 65 million years ago. Now, I didn't go into the late and the early, but remember, each of those different periods, your Pennsylvanian, Mississippian, Jurassic, Triassic, all of those are broken down into early and late. But if I sat here and rattled them off, this video would be even longer than it is now, so I saved you guys some time. But don't worry, we'll talk about it more in class. This was a broad version of the geologic timescale. It was generalized to the world, not specific to New York. So in the next video, we're actually going to delve into the New York geologic timescale a bit further, because is it going to look exactly the same as the rest of the world's? To an extent, but we're going to have some things that they don't. So we're going to get into more specifics in that video. As always, if you have any questions, please don't hesitate to reach out. Bye!